What is integration and why should we care? What the integral of a function means depends on context, which also helps to explain the why of an integral. Typically, it refers to transforming a function into a scalar quantity that describes some type of important aggregate behavior of the function over a set. It is kind of like summing up the behavior of a function over a set in order to make important inferences. Some examples of what integrals mean in different contexts are given below. In probability theory, the functions that quantify scalar outputs of an experiment are called random variables. The integrals of random variables, weighted by their probability density functions, give the expected value of the experiment. Other standard statistical quantities, such as variance, also involve integrals. In engineering, design, and manufacturing processes, it is often important to compute the length of a curve, the area of a region, or the volume of an object. For example, to determine the amount of resources or cost in constructing an object. Such quantities are given by integrals. In physics, integrals are used to determine important quantities like velocity, which is given as an integral of acceleration, and displacement, which is itself an integral of velocity. In finance, integrals are sometimes used to determine options pricing. Many models of complex physical phenomena involve partial differential equations that are solved via numerical methods, for example, finite element methods, that require computations of many integrals to construct accurate approximations. And then in data science, statistical machine learning, and any other data-driven discipline where proposed models are fitted to data, the goodness of fit of a model, a loss function, and other important quantities can usually be described in terms of an integral, or at least its discrete counterpart, summation. So that's really what an integral is. It's depending on the context, but it's a very important quantity that shows up all across the data and computational sciences. There's some important notation that you should understand, which is that we are integrating a function over its domain. So if we have a function f of x and we take a set A as a subset of the domain is just the inputs, the points that are viable inputs to the function, where the function is actually defined at those values. Then the integral of f over a is denoted by this. So this is like an elongated s. If you want to see what it looks like, you can open it up. It's int with a backslash int. I'm making this large, of course, and it looks like an elongated s because it's kind of like an infinite summation. So that's a good way to remember the connection between integrals and summations, is that it's kind of like an infinite summation. So you're taking the integral over a of f of x. This is a very simplified, clean notation. You'll see other notations elsewhere. There's actually no universal notational convention. This is just the one we're going to use for simplicity in this notebook. Here we provide a standard motivating example that helps to illustrate some of the ideas and make this all a little bit more concrete and less abstract, while also avoiding complicating calculus details. So here's the general setup. Suppose v of t describes the velocity of an object moving either forward or backward on some path over the time interval t naught to tf. T naught, also called t sub 0, denotes an initial time, and t sub f the final time. Suppose we are interested in how far along the path the object ultimately ends up relative to its starting position. In other words, we're interested in the displacement from the initial position. This is given by an integral, the integral over that interval of time, t naught to tf, of v of t. So that's the concept. Here are some examples with very intuitive solutions. For simple functions of v of t, we can either easily conceptualize the problem and intuit the solution with little difficulty. In other words, without referring to anything from calculus. Consider the following scenarios. V of t equals 0. In other words, the object is not moving. Well, guess what? The displacement, how far away it is ultimately from where it started up, is 0. That's it. It didn't move. The object didn't move. This is not surprising. So the integral of 0 is 0. Okay, big surprise. Suppose now that v of t is equal to 5 if t is between t naught and the midpoint of time between t naught and tf. And then suppose that it's negative 5 for the other half of the time interval, for the last half of the time interval, from tf plus t naught over 2, that's the midpoint of the time interval, all the way up to tf. I'm not even defining what it is at t naught or at tf, because as it turns out, defining a value at a function at a single point doesn't change the interval at all, so we just won't even worry about that. But this simply means the object is moving forward at a constant speed of 5. We're completely ignoring units of speed here. So miles per hour, feet per second, kilometers per hour, doesn't matter. Just a speed of 5, just forget all the units, for half the time. And then it's going to move at the same speed but backwards. In other words, in the other direction, the other half of the time. In this case, also the integral of v of t is 0. The ultimate displacement, the final displacement from the starting position, is 0 because the object just did a simple round trip back to where it started. That's it, because it went forward at a speed and it went backwards at the same speed over the same amount of time. So of course it ends up where it started. But suppose we have the same velocity as the previous example, but now you go, well, I don't want to know the displacement. I want to know the total distance traveled instead of just the final displacement. Because when I leave in my house and I get in my car and I drive to the store or to school or wherever it is, and I drive back maybe on the same exact route at the same speeds, my odometer doesn't say I didn't travel anywhere. It says how far the total distance I traveled. Well, then what you want to know is the integral of the absolute value of the velocity. That's what you want. But what is that? Well, in this case, we know that this means we are integrating a function that is constant over all time, because the function v that we're talking about was either 5 or negative 5. So now it's just 5. So if an object moves at a constant speed is the absolute value of velocity, then we should be able to figure out the total distance it traveled. This is easier now when we consider units. So suppose v of t is described in miles per hour, which we write as miles divided by hour. It sure seems like if we just multiplied by the total number of hours the object was moving, then we would get the total number of miles the object traveled, because miles divided by hour times hour equals miles. It's kind of a dimensional analysis of the units. In other words, the hours cancel out, right? It seems like you just want to cancel them. Like if 1 divided by 2 times 2 and the 2 cancels out, you go, wow, it's 1. Same idea. So in this example, the integral of that absolute value is 5 times the length of time that it was traveled, assuming that the time units are also in hours. So we'll say tf minus t naught, assuming that those were in hours. So now we can move on to visualizing the results. Since we're again interested in some visual data storytelling around actual problems that come up in computational data science, we move towards code to help us visualize results. To that end, from Matplotlib, there's this patches module, and it has things like polygons and rectangles and a patch collection, but that's from collections. That's all very useful for visualizing things involving integrals. So I'm going to import all of those, and now I'm going to define that velocity function that assumes you have a tf and a t. I'm going to assume t naught is 0 for simplicity. And then in that case, I'm going to look at the time value, and if it's less than half the final time, because I'm assuming t naught is 0 again, then the the velocities, right, for the v, the velocities over all these times, for those velocities, it's going to be 5. And if it's on the first half of the interval and otherwise it's on the back half of the interval, it's negative 5. So it's a pretty simple function, and I'm just looping through all the i's that I have for the length of the t array. I'm assuming I'm given an array of t values, and I need to compute the corresponding velocity values. That's all I'm doing there. All right, so now I set things up. My t naught is 0. I'm going to say tf is 10 just for the sake of simplicity. I'm going to use linspace. The default with linspace, I believe, is 50 points. Yep, so you can see the number is 50 points there. And I'm going to create then that array of times. I'm going to create this figure in the axes for a subplots, just number at 0 for simplicity. I'm going to go ahead and plot t and the absolute value of v of t, and I'm going to plot that in red. And then I'm going to set my the bottom y limit to be 0. And then I'm going to grab these t values. I'm going to shade the region associated with the integral, because this integral is basically the area under the curve, which is something that will really be emphasized when we see these plots. So I create these these t values and these I values for the integral. That's why it's IT and IV, because they're for the integral. And then I create these vertices. Notice I use this star zip. That might look familiar from a previous notebook. So these are a bunch of vertices where then I create a polygon that connects everything in terms of all along the curve, the V of t values and along these IT values. So I'm basically just creating a polygon associated with the curve in the horizontal axis. That's what I'm trying to do here. And then I add that as a patch, and then I have some text here that describes what the integral should be. Notice I have to use a raw text here for some tech that I have to display the math. And then I don't want to have those little spines, little tick marks showing up, but I do want to set like some particular T0 and TF values in terms of labels. So that's all that I'm doing here. And you can see this is the plot. So I've shaded that region. That's that polygon that I've added a patch. The face color 0.9 is just related to kind of how gray I basically want this to be. And the edge color 0.5 is related to that boundary value plotted. There's that absolute value of the velocity at a constant 5. And I'm just labeling T0 and TF here. So I'm just giving a visualization of that problem. This is, again, a lot, a decent amount of code, about 10 or so lines that are involved with visualizing what's going on with this object. And so now you can see there's just this rectangle, right? This constant velocity over this time, the area of the rectangle is what the integral is. That's exactly what it is. And if I plot the actual function v, and I do the same thing where I'm making polygons again, but I won't get into all the details, I'll just show the result. Here was the non-absolute value of the velocity, and you see you have two rectangles here. There's just one above the horizontal axis. This is where the velocity would be 0, and one below the horizontal axis. So there's something that we're seeing here with these plots that really indicate what's going on with integrals. What is it that we see? It appears that these integrals are simply related to the areas of the shaded rectangles. In particular, the integral of the absolute value of v of t is exactly the area of the single shaded rectangle. That's exactly what this is. It has a height of 5 and it has a length of TF minus T0. That's exactly what it is, and that's what the integral was. And on the other hand, the integral of v of t is given by the area of the rectangle above the t-axis minus the area of the rectangle below the t-axis. These areas seem to cancel each other out. In fact, if we think of areas as being signed so that any area below or above a horizontal axis is negative or positive, then we can see that the integral of v of t is just the sum of the signed areas. These observations actually lead us to a useful conceptualization of integrals in terms of sizes of positive and negative regions of a function over a set. Below, we visualize what the sign of an integral is for a function in terms of what dominates, the positive or negative areas. That the quad, and then we use the quad function to compute accurate approximations of the integral. So some key takeaways about quad. What is this quad I just mentioned? The quad function is within the integrate subpackage, a sublibrary of the SciPy library. And you should take maybe 5 to 10 minutes to review some of the documentation here about the quad function and what it does in terms of integrals and how you set things up. It's kind of interesting. There's all sorts of information you could read about SciPy, and you can see there's a lot of documentation that they have about this, and then they have lots of examples that show how to calculate. And you can put all of these, you could test this, you could put this into the notebook if you want, just copy and paste some of the code, get rid of these signs here. These are just coming from effectively like doc tests that are inside of the source code for this. And you could see that if you want to see how even this page is made. If you come up here and you click on the source code, you'll see that for this function, there's a doc string that says what this function is. It has documentation about the parameters and the returns. This should look familiar. And then it has some notes about what's going on with it. And if you scroll down, you'll see that it has these examples about calculating what this is. And these look just like what I had you do for doc tests before. All right, so quad function, what does it do in the end? What you need to know is this. It returns a tuple as an output, much like our compute bisection function I said from the previous lecture notebook. It's actually from the first part of this notebook. So I'm going to go ahead and fix that. Let's see, from the first part of this notebook. We're going to find it from the first part. There we go. From the first part of this notebook. Bear with me. Part of this lecture notebook. There we go. And I'll just click over here. There we go. Sorry about that. Bear with me. Okay. So it, just like the compute bisection produced a tuple as an output with A, B, and C, the quad function has a tuple as an output. The first component is the approximation of the integral that you want. The second component is an approximation of the error in that integral. Therefore, we usually append a 0 to it, to the end of the call, whenever we are just interested in the actual approximation of the integral. And you'll take a note of this below. Kind of like with compute bisection I showed in an earlier video, and I have it in code above in this notebook, we would perhaps append a square bracket with a -1 to just take out the root approximation that we wanted. If you peruse the source code of the quad function, you will see nice docstrings.txt. I already talked about that, and I have some links here directly to that source code, which I already showed how to get to. The integrate subpackage is itself really interesting and is useful to familiarize yourself with. So you can click here to read more about the integration subpackage, and there's like the quad function, the double integration, the double quad for double integration, triple quad for triple integration, fixed quad, there's all sorts of things for doing different types of integration rules, and they have a nice kind of tutorial here that just guides through examples of how to calculate all sorts of different types of integrals. It's really neat. So the way you use that is from scipy.integrate, you should import quad. The reason we're doing this isn't the algorithm we're going to pursue, but it gives us a value by which we can compare the algorithms we will use to estimate integrals numerically to some accurate estimate of what the integral value is. So it's just a means to an end for us. We're using it just to get a good estimate of what an integral is. So when we have this function here to plot an integral for a function f, and we want to plot it from x min to x max, and we want to use a to b to be the interval where we integrate over. It's kind of like with the root finding, where there's a range of values we might want to plot, but in an interval a to b where we look for a root for a function f. It has a lot of similar features to root finding. Well, now the integral from a to b, which I store as int underscore ab, is just quad f a b. That's how you use the quad function. You give it a function, you give it the limits of integration, a to b, the interval, and now I just want the value of the integral. I don't care about the estimate of the error in that approximation. This is it. That one line of code is estimating the integral of the function f. Again, this is just for reference, ultimately for us, for the purposes of this part of the notebook, but it's just really important to emphasize. Now we have our computation of the estimate of the integral of f, and everything below is just plotting. I'm just creating information to plot the function and to kind of shade the region under the function using this kind of polygon function in order to visualize what's going on with the integral. So everything below is just for plotting, and it's just based on what you kind of saw above, just encoded inside of a function. So I create my plot function, and now I can interact with that plot function. I can feed it fixed lambda functions, and is using this widgets.fixed. I could have also just done fixed. I don't know why I'm doing widgets.fixed here, but I am. And so now I can run, I can say, okay, here's the function I want to look at the integral of. X plus 1 times x minus 5 times sine of 3x. Why? Because it's an interesting looking function, that's all. Excuse me. I'm going to fix the x min and x max, so the region of the function I'm plotting from -1 to 5. But I'm going to allow the limits of integration to change. That's what the a and b are for. And then I'm just fixing the figure number so I don't create new figures every time I run interact. So now when I run interact, I say, okay, here's my function, right? It has kind of an interesting looking feature to it. And when you look at this, you'd say, oh, the area under the x-axis seems to be more, if you look at the shaded gray area, there seems to be more of the shaded gray area below the x-axis than above the x-axis. And you see, oh yeah, the integral is negative in that case, because there's more negative area. If I was to reduce a, here's the a and the b, if I was to reduce a over here, so let's just go ahead and move it over a bit. Let's say to 1.4 and run interact. Now you notice that the integral is positive. There's enough of the positive area to not only cancel out this negative area, but to even be left with like an additional positive amount. So there's more positive area than negative area. Now if I shrink the b, so I move this right endpoint over more to the left, then I could potentially remove some of this positive area, and then maybe it looks like this is more than that. So let's just kind of see if I move the b just a little, so like 3.6. Okay, so the area is still more positive than negative, but it's a lot smaller, 0.55. Shrink b a little bit more. Now it's negative. Now it definitely is clear. There's more of this negative area than this positive area. But if I shrink b too much, now I don't have too much negative area, more positive area, and the integral's more positive. It's 3.24 now. So you can just play around with this, and you can make sense of how this code is working in terms of what's going on with the figure. A lot of this is just plotting like the x-axis and making like kind of tracking points along this curve and the axis here in order to shade it in. That's all this is doing right here. So feel free to play around and add more comments, and you can play around with new functions. But the point of this is now we have a way of visualizing a function, annotating a plot in terms of adding a title with an integral, as well as shading in area to describe the meaning of that value, why it's positive or negative in terms of the amount of signed area. So we have some visualization to go along with the concept of what's going on with an integral. This will really help us moving forward when we go to approximate the integral using some numerical means that are easy to code up, basically rectangular methods. So that will be coming up in just a second. But before we go to the deterministic rectangular methods, we're going to create a My Functions Amazing class. And this is going to inherit from My Functions Enhanced class, which inherited from My Functions class. So My Functions Enhanced had all the stuff with roots. I'm just kind of pulling everything together to say a function is something that you might want to study the roots of. It's also something you might want to compute the integral of. So as a suggested activity, you could add docstrings to the integration class below and add comments to this class. So just like A and B for an interval might be where I want to search for a root, it could also be where I want to work with an integral. And so I'm initializing this just like I initialize My Functions Enhanced, although with less other parameters because I don't have any, I'm just doing this for the integration, but it's inheriting all the other stuff that came with root finding from this class here. So I'm initializing it. I have a set integral limits, just like I had a set, bisection parameters method. I have a set integration limits method, and that just sets the A and B values. I have an evaluate the integral method, and as long as A and B are both not none, what it does is it uses that quad function with those data attributes of F, A, and B, and it gives me that first output of that quad function, which is the approximation of the integral. It creates a new data attribute called self.integral, and I'm assuming that when you go to evaluate it, you actually want that return like printed to screen. So, I mean, this just returns the value. Maybe you want it for some other purpose. You could add, this isn't printed to screen unless it's the last thing in your code. So maybe you want to add a print statement here. And then I have this plot integral method, which involves all that stuff I showed in the plotting involving, it's just collecting things to create the polygon to shade everything under the curve. And then I have a method to evaluate and plot the integral. And what it does is it just calls the other methods. So if everything's set and ready to go, you evaluate the integral at the A and B values that are passed to this, and then you plot the integral. That's all it does. So it's just calling those methods. So that's a pretty simple class, actually. I mean, I know it looks like a lot of code and I went through it kind of quick, but I think you're getting used to it. A lot of methods are kind of very small, and they're just parsing out things in a very kind of thoughtful way so that each method does a very specific thing in terms of setting specific data attributes or creating certain visualizations. And also I'm inheriting a lot of things that I already built up in other classes that I'm subclassing this from. So now when I create my F integral object from My Functions Amazing, and I look at that lambda function that I was just looking at, the x plus 1 times x minus 5 times np times sine of 3x, now I can, here's the fun thing, this is a function, or excuse me, this is an object that I've created from this class, but I can interact, like I can run the widget to interact with the method attribute of that object, the evaluate and plot integral method attribute, which is kind of doing all the stuff that I was doing in this plot integral function that had all this other stuff. And I'm just doing it now on the method attribute. because the evaluate and plot integral is just doing what that plot integral function was effectively doing. So when I run that on, again, the f integral method attribute evaluate and plot integral, and I run interact, you just see it's the same types of plots as before. And so now this is really useful, as you can say, okay, I can create a function object with my functions amazing with some lambda thing here, and then you can immediately start exploring that that amazing function object. You can start exploring potential roots of it. I mean, this function has lots of roots you might try to estimate. You could start just plotting it and getting an idea of where the roots are and how you want to estimate them and do the bisection algorithm. You could start playing with the evaluate and plot integral method of it and get fancy visualizations for it. It has all sorts of features that are in terms of method and data attributes that are really useful for you to play with that function in order to answer all sorts of different types of problems that might arise in the study of that function. So that's kind of it. That's the whole point of just creating that class. It helps set up the next things, the next set of stuff we're going to do, and just organizing things in classes and objects. But before we go and end this and then move on to the next video, which will discuss the rectangular methods, these geometric deterministic methods for estimating integral, I want to emphasize that context is everything. And these are just one-dimensional examples. So above, we have just looked at functions with univariate inputs, meaning there's basically one variable that's the input, and one is a scalar variable at that. Subsequently, we observed that the integral is related to the signed area between the curve defined by the function and the axis defined by the input. This observation can be conceptually extended to functions with multivariate inputs. Suppose f of x is a real valued function, but x is now a point in the Euclidean plane in R2. Then for a set A that's a subset of the Euclidean plane, the integral of f over A is related to the signed volume between the surface given by the graph of f of x over A and the horizontal plane defined by the two-dimensional input space. Now maybe if you haven't seen this before, those are just words that maybe don't have a lot of meaning. It's a little harder for me to plot. I could do it, but it's not really the point here. You can also generalize the concept of area and volume to describe integrals in geometric terms when the inputs are three-dimensional or even higher. But we can pretty much stick with one-dimensional examples to explore the typical numerical algorithms used to estimate integrals. Although some of the strengths and weaknesses of these algorithms are not apparent until you get to higher dimensions. And I just want you to keep that in mind, because you could definitely be led astray in thinking that, oh, this integral method, like particularly that we might use, is the best one to use. But you might find that, well, yeah, that's great if you're dealing with the integral of a function over a one-dimensional space. But maybe it's really not good if you're trying to integrate a function over a 10-dimensional space. And that happens. So I talk a little bit more about that in the external activities notebook, which we'll get to after this, obviously. You'll do this lecture notebook first. And I'll talk about Monte Carlo methods, which are kind of like a random way of estimating an integral. So that's it for this particular part of the video, and I'll now discuss how we estimate these areas, just like how I talked about how we estimated roots below.